So welcome everyone to our presentation today on store-to-leak forwarding there and back again. We'll start this presentation first with a little bit of introduction. My name is Claudio Canella. I'm a PhD student at Graz University of Technology, and you can always find me on Twitter or reach me by email.
My name is Lukas. I'm also a PhD student at Graz University, and you can also find me up there. So today we're going to be talking about, for one thing, how loads handle previous stores. And then in the second part of the talk, we're going to look at how Meltdown was mitigated in hardware. And for both of those, are there new attacks that we can come up with? And lastly, can we mitigate those attacks, and can we do so efficiently? So because all of you are experts anyways, we're going to skip most of the boring background and we'll jump straight in. We'll look at the memory subsystem first, so we're the front end and the execution engine. And the first contact of the execution engine with the memory subsystem are the load and store buffer connected to the load ports and store ports in the execution engine. And then we go on to the L1 cache, the TLB, and so on. And then we go to L2 and off-core finally to L3 and DRAM. But what we're going to be focusing on today is the store buffer and the load buffer to some extent. So let's look at how a store works. When we write data to an address, the store port just hands it off to the store buffer, and that's already a nice little optimization. And because the store port is then free again, and the store buffer will handle the rest. So the store buffer will eventually propagate this data on to the L1 cache. Now, something a bit weird maybe, what happens when we, right after storing, read from this address again? So the load port sends a request to the load buffer, and then the load buffer could look into the L1 and see if the address is already in there, and if it's not in there, look in the L2, the L3, and so on. But now we have a bit of a problem, right? Because we might have just stored, and we have a new data in the store buffer, but it's not in the L1 yet. So for this optimization to work, there's another clever little thing called store-to-load forwarding. And so when the store buffer and load buffer need something, it can also look in the store buffer and then get the data directly from there, which is of course much faster. So in this example, we store it there and then we read it back again. So what does this logic look like? We have 4 cases in 2 categories. We have to choose, we have true positives where the address correctly matches and data is correctly forwarded, and the negative where the address doesn't match, and so we don't get any store-to-load forwarding. And this is where our attack, store-to-leak, will live, between those 2 cases. And then the false cases, where we have a false positive, where the address doesn't actually match, but we still get forwarding. And this is the case in fallout, the right transient forwarding. And this is because we can have some lower bit congruence of the addresses, and so the CPU falsely forwards. And then the final case is a false negative, where the addresses actually match, but the CPU decides not to forward anyways. And this is spectre STL. So this store buffer match logic is entirely transient, right? So if something is correct, incorrect, if one of these assumptions before was incorrect, then it doesn't matter architecturally. It all gets thrown out anyways. But for us, for store-to-leak, we actually, as I said, only look at the left column where everything works correctly. And something really interesting, and for us crucial, is that stores are only forwarded when they contain valid addresses, valid physical addresses. And now, of course, that makes some amount of sense, because why would we want to store or load from an invalid address? And the Intel manual also reflects that. It says that the store buffer entries are filled with data, linear address and physical address, and the forwarding only happens once we have data and address. So a virtual address is then valid when it is physically backed. And the permission checks, this is something a bit special about Intel CPUs, happen not exactly when they should happen or at the earliest, but they happen at some point. And during this, we still get out-of-order execution on the data. And this is, of course, what Meltdown exploited. So what happens when we do store to load on inaccessible addresses to us, like kernel addresses. So let's take a look here. We just write something to an address, kernel address, we write an X there, and then as expected, we get a fault. But out of order, our next instruction, which is a read, and then a dependent access to memory, still happens. So if this happens, and if we can later detect this access in our memory array, then we actually got store to load forwarding. And we might have learned something here.
Okay, but what do you want to attack with that?
Right, so I'm just going to throw out an example here. Kernel address space layout randomization. Every time we boot, the Linux kernel puts itself, or the kernel is put at some random offset in a fixed space. And the same goes for the modules. Every time we boot again or load modules, they get placed somewhere else. And so now maybe, why don't you build the attack here?
Okay, yeah, I think with your explanation, I can build this attack. I think, let's call it data bounds. And we have here a very simple code example. We have here on the bottom, we have our memory array where we want to encode what data was that we loaded. Then we have the possible offsets of the kernel with the blue one indicating where the kernel is actually placed. And just a very simple code snippet. We write to a location, it's a kernel address, and then dereference that same address, right? Based on your explanation, we should get store to load forwarding at one point. So let's just try that. In the first example, we see that there is nothing mapped. Yeah, so based on what the description is, we cannot get store to load forwarding because we cannot get a store buffer entry. And we can repeat this and nothing ever happens. Until at one point, we see that there is something mapped. So now we can get a valid address, we write our X there, we can get a store buffer entry, and when we then load from this address again, we get store to load forwarding, and now we could see, or we should see, this hit on the memory. So the question then is, what if an address is valid but unknown? So we know that the address is backed by physical memory, but the information that it is backed is not known to the CPU currently because there's no TLB entry. So based on this, if we repeat data bounds, we should learn something, because if it is forwarded on the first try, then we should see, or then we learn that it was in the TLB. If it is only forwarded on the second try, then we know that it is valid, but it wasn't in the TLB the first time. But with the second try, it is now in the TLB, and we learn this information that it has not been recently used, for instance. And if it is not forwarded, yeah, then it's simply unmapped, like we've exploited in data bounds itself.
Right. So let's separate these cases out, and we have a new attack primitive here, right? And so we'll give it a new name because we need a name. We'll call it fetch and bounce, because now we acknowledge that someone at some point actually has to do the fetching if we want data bounds to work. And this is as Claudio explained, this we can see by the TLB. And so on a concrete example, if you try this on kernel pages that are all valid, then we can see that when we first try to look up in the TLB, there is no entry. And then we won't get a store buffer entry, or we won't get store to load forwarding, and we won't see anything. And the same for the second address. Again, there is no TLB entry. We won't get store to load forwarding, and the entries are only created later, but not in the first transient window where we tried. And so now when we access the third address, there is already a TLB entry. And now we get store to load forwarding within our first access, and the X gets encoded into memory. And so now, as Claudio said, we've learned something. We've learned that the operating system, or anyone really, has touched this kernel memory before, recently. Yeah. So with this, we can observe kernel activity. The kernel itself isn't a very interesting target because it's only a few pages. But the modules, on the other hand, are 4 kilobyte pages and can be quite large. And so when we pick out a module here, let's say the Bluetooth module, and we look at just any code address, for example, and we connect the phone to it. Now, whenever we sample with fetch and bounce, we can actually see activity in this module.
But can you actually show us this? Because you just claim this, right?
So you're basically getting at the old saying, proof of concept or leave.
Yeah.
Yeah, right.
Modified version of that.
Yeah. So of course, okay, I can show you. So a step I've skipped here is how we get the Bluetooth module address in the first place. And so for this, we actually go back to data bounds that Claudio explained. But now we do it on the address space that the kernel modules are located in. And we'll do this for each page and see if it's valid. And when we get an amount of contiguous pages, we know that this is one kernel module, because kernel modules are always separated by empty pages. And so let's look at this in the video. We start this mapping tool, and we can see that this was the entire scan. It's very quick. And now in a secondary step, we process these addresses, and we look for 3 modules here. We look for Bluetooth, Wi-Fi, and Thunderbolt. And this spits out then the addresses that it found, and it thinks these modules are at. And so now we're going to compare this to the correct addresses in proc modules. And so we see for the first module, the Bluetooth module, we have a correct hit here, a correct address. For the second module, the Wi-Fi module, it also worked. And for Thunderbolt, it worked as well. And of course, because this is how we identify them, the addresses, the sizes are all correct as well. So we can actually only identify modules with unique sizes with this. Okay, so that's the first part of the attack, right? So now we know where the module is located from user space, because the kernel doesn't tell us without root. And the second part now is sampling this kernel module. And the problem here is that the TLV isn't shared between cores. And the kernel module can run on any core. And we don't actually want to do this fetch and bounce the entire time in a loop on all cores, because then nothing else works. So what we're going to do is jump from core to core, sample with fetch and bounce, clear the TLV, and go to the next core. And so this is what we see here in this demo. We have paired our phone, and first we see no detections here. And when we press play, we immediately see a detection. So in the left column, we see our hit rate. And in this case, it's around 1%, because we sample much more than apparently the Bluetooth module accesses this page. And in the right column, we see just a single threshold. And something to note here is that the detection is very stable. We always get ones when the music is playing, and we always get 0 when it's not playing. And a peculiarity of the Bluetooth module here is that even after we press pause, it takes a bit longer to actually stop. So we assume there is some after activity going on here that is not related to our actual attack. But when we start, you can again see that this is a very immediate detection, because the resolution can actually be quite high. Yeah.
Okay, now I believe you.
Thanks. It's very nice of you.
Yeah, I'm generous.
So we actually have a third variant of this, and that's when we combine fetch and bounce with Spectre. So normally with Spectre, we have something like this, and instead of the kernel array, we have an oracle that is attacker controlled. And so in this case, we have just any kernel memory access that is a dependent access on a bounce check inside an array. And when this access happens, some kernel page is loaded into the TLB. And this then we can later scan the possible pages here with fetch and bounce. And the advantage this brings over flush and reload based Spectre attack in the kernel is that we don't need to control this oracle, we don't need to have access to this oracle. And yeah, I think these are our primitives for store to leak forwarding. And now Claudio is going to look at his newer work, where maybe he's going to tell us something about Meltdown.
Yeah, so we all know that Meltdown needed to be fixed, and the software workarounds were a bit costly, so obviously they have been fixed in hardware. And we started out with 2 assumptions when we looked at these mitigations, because nobody told us how they work exactly, so we needed to reverse engineer them. And our first assumption is simply that stalling the CPU might be too costly, which I guess is a valid assumption. And in the second assumption, we just say, okay, these hardware mitigations were available quite fast, so we assume that you need a lot of redesigning in the CPU pipeline, and you cannot do that easily because you need to verify that you don't break anything else. So our hypothesis is simply that the load is still executed, but the return value is simply zeroed out on false. And we wanted to verify this hypothesis, and we performed 2 tests. And the first one is we simply performed a meltdown attack, because that's what it is intended to mitigate. And if we simply read zeros, then we can be partly sure that this is really what's going on. And we actually tried this, and we only got zeros, but we further wanted to support our hypotheses, so we can use the second test where we used performance counters. So we looked at different ones. In the first test, we looked at memory stores that are caused, or stores that are caused by memory accesses. We compared it with unaffected AMD CPUs, and as we can see on mitigated and vulnerable CPUs, there's no difference between user and kernel addresses in the stalling behavior. But for non-present pages, we always stall. And on the unaffected AMD CPUs, for kernel pages, we also stall. So this is a first indication that we might be correct. Second one is then we looked at the number of issued microops on the load ports. And we can again see that for user and kernel addresses on mitigated and unmitigated CPUs, it is roughly the same. And in the third test, we simply looked at how long do we need to wait for this data to be available. So are we actually loading the data first, or is there the zero just passed on from before we access the memory from some internal buffer? So without mitigations, we can see we have more or less 211, 206 cycles that we need to wait for the result. And on mitigations, the number is the same between kernel and user pages. The difference in the timing is simply with mitigations is a faster CPU. So yeah, that's why the result is there smaller compared to the CPU without mitigations. With these tests, we can now more or less be sure that our hypothesis is correct. So the question then that we asked ourselves, can we now build an attack with this? And the answer is yes. We called the attack EchoLoad. It's again a fast and very reliable KASLR break. And it again uses the cache to encode the returned value and we later retrieve it from there using flush and reload. If we try to visualize how this works, we have this very simple example. We again have on the bottom the location of the kernel and the possible offsets where it can be mapped. And we simply perform a memory access. If nothing is mapped there, we observe the stall. And this happens for all memory pages where it is not mapped, or memory locations where it's not mapped. And the location where the kernel is actually mapped, we load from there, but we do get a zero from there. So now simply by observing this zero in the cache, we can be sure that our kernel is mapped there.
All right, so how fast is this actually? Do we have to wait an hour for our KASLR break?
No, so EchoLoad is actually quite fast. We evaluated it on several CPUs. In the paper, we have a lot more CPUs than those 3. But as we can see, it also works on older CPUs. There it's basically Meltdown. And we also tested it to suppress the fault. We use speculation, TSX, or sec fault handling. And as we can see on the i9, with TSX, we need to wait roughly 29 microseconds for the result and an F-score of 1. So we are more or less perfect. And with speculation, we don't always get a value of 1 for the F-score, but this is simply because we sometimes fail inducing the misspeculation. So the nice thing about EchoLoad then is also it works in SGX and also in JavaScript. And with that, now we want to look at the final part. And this is how can we prevent these microarchitectural attacks on KASLR? There have been quite a few in recent years, and we started out by looking at the commonalities of these microarchitectural attacks. And this analysis showed that there's timing difference between mapped and unmapped pages that we need to mitigate. We have a timing difference for different page sizes. And there's also a timing difference between executable and non-executable pages. And to be able to mitigate all of these attacks, we need to consider all these things. So our proposal was called FLARE, Fake Load Address Response. And if you take a look at this, we can see here the current Linux design where code and data is simply in one block, data follows the code section. They use different sizes for the memory pages. And in our first step, we simply mitigate the difference between mapped and unmapped pages by filling the whole address space so all possible offsets with pages. And all of them are the same page. So also code and data now use the same size for the memory pages. In the second step, we want to mitigate the difference between executable and non-executable pages. And for that, we simply split the memory, the 1 GB memory range in half, fill the first half with executable pages, place the code section there, and the second half with non-executable pages and place the data there. So how does this then look if we perform EchoLoad on this page? Here we fill out all everything with the same type of memory pages, and now we get a 0 everywhere. So contrary to before, we more or less hit the needle in the haystack. And if we take a look at all the other attacks, we also see here that with FLARE, you cannot differentiate the position of the kernel independent of which attack that you use, be it page sizes, data bounds that we've seen earlier, the double page fault, which also uses the DLB, Dr. K, also the DLB, and Fallout. Now you can find a proof of concept implementation of FLARE on our GitHub page. And with that, we have more or less reached the conclusion of our talk. And to conclude, I would like to say that optimizations do introduce security problems that we need to consider.
And even when we mitigate them, sometimes there's a little edge case left, and maybe we can still exploit that.
And finally, we once again require software workarounds to prevent these little edge cases from causing additional security problems. With that said, thank you for listening, and we hope that you enjoyed our talk, Store to Leak Forwarding, there and back again.
Thanks, and we'll be available for questions now probably.